Today we will talk about the methods we use to identify the ages of rocks, and also we will discuss a little more detail about geologic timescale. First, let's start with reviewing the basic atomic structure. We know an atom has two basic parts. One is nucleus and the other one is the orbits. Nucleus contains the protons and neutrons, which basically are building up the mass of the atom. But most of the volume is actually created by the orbits, which hold the electrons. The atomic number is the number of protons in the nucleus. And the mass number is the number of protons and neutrons in a nucleus. We also have some isotopes of different atoms having the same number of protons and different numbers of neutrons in their nucleus. Some of these atoms may not be stable enough to hold up their nucleus structure, and they actually may get changed in time by different activities. So the activity of these unstable atoms is called as radioactivity. So the radioactivity is actually a spontaneous decay in the structure of an atom's nucleus. Here in the picture on the right side, you see the decay of uranium down to lead. Let's just talk about the types of radioactive decay before moving any further. There are basically three different types of radioactive decay. First of them is alpha emission. In this case, there is an alpha particle ejected from the atom. And an alpha particle contains two protons and two neutrons. So as you see in this picture here, we have a group of two protons and two neutrons in the nucleus of an unstable parent atom. And when this alpha particle emission happens, these two neutrons and protons will leave the nucleus. In this case, the atomic number is going to be lowered by 2 because we are basically removing two protons from the nucleus. However, the mass number is going to be reduced by 4 because we are removing total 4 of two neutrons and two protons. The second type of radioactive decay is called as beta emission. In this case, there is a beta particle, which is actually an electron, is ejected from the nucleus of the atom. So in this case, we again have our unstable parent nucleus of the atom. And then here we have a proton, and we will have an electron emission. So we will remove an electron from this system. In this case, atomic number is going to increase by 1 because a neutron is going to turn to a proton by losing its negative charge. And now it's going to stay as a positive charge proton. But atomic mass is not going to change because we still have one proton instead of one neutron. We actually switch to a proton. The third type of radioactive decay is electron capture. In this case, an electron is going to be captured into the nucleus. Here again, we have our unstable parent nucleus, and we have here a proton. When this proton gets a negative charge from this additional electron captured by the nucleus, it is going to become neutral. So it is actually transform itself to a neutron. In this case, since we will be losing a proton from the nucleus, atomic number is going to be reduced by 1. However, instead of losing that one proton, we are earning a neutron. So that means the atomic mass isn't going to change because the total number of protons and neutrons are going to stay the same. So let's talk about a little more detail related to this radioactivity processes. With radiometric dating, we use the decay of these isotopes in rocks to calculate the age of the rock. And half-life is a very important process that we need to consider when we are doing these calculations. So a half-life is the amount of time required for half of the radioactive isotope to decay. Basically, every half-life after every half-life passed by, we'll be losing half of the mass of our unstable atom. And that mass is actually going to turn to some daughter atom, which is going to be the product of radioactivity process. So radioactive parent isotopes are going to decay to stable daughter isotopes. In this case, we expect the amount of daughter isotopes increasing while the amount of parent isotopes decreasing. And as I said before, every half-life we will lose half of the mass of the parent isotope and we will earn the other half of the daughter atom. So here in this figure, you actually see that this decrease or increase in the masses of daughter and parent atoms are exponential. So when we have the ratio of parent to daughter is 1 to 1, that means one half-life has passed. And after two half-lives has passed, we will have this ratio being 1 to 3. And it goes on like that. For radioactive dating, we use various isotopes. And with each passing half-life, we lose 50% of the remaining parent material, which will decay to daughter atoms. As the parent atoms decrease, the daughter atoms increase. We use several naturally occurring radioactive isotopes for dating rocks. Here in this table, you see several examples of that. For example, we use uranium-238 or uranium-235 and follow their decay to lead-206 and 207. And as you see here, the half-life in terms of time is actually a real big number. We are talking about billions of years for losing the half of the mass of uranium and converting it to lead. And also we can use thorium and rubidium. There is also potassium and argon that we can use for dating the rocks, which is actually especially important because potassium is one of those chemical elements that we have a lot in the rocks. And it has a half-life of 1.3 billion years. That means we actually can date rocks as young as 100,000 years by using potassium decay to argon. And potassium decays to argon or calcium. The calcium part isn't very useful because we all know that we have a lot of calcium naturally occurring in those rocks. And argon itself is a gas, and it also might be a little problematic to use because as a gas, when it is going under some high temperatures, we can easily lose that gas from the rocks. In these cases, for having a successful radioactive dating, we need to have both parent and daughter material staying in the rock trapped all this time. As you can understand from this statement, radioactive dating is a very complex process. Determining the quantities of parent and daughter isotopes must be real precise, and in this case we are talking about counting atoms. And some radioactive materials do not decay directly into stable daughter isotopes, like here in this picture. As an example, uranium-238 has 14 steps to ultimately decay the most stable daughter of itself, which is lead-206. And in each of these decay processes, we will get either an alpha or a beta emission. And as I said before, dating with radioactivity is a very delicate process. There are a lot of sources of error. First of all, our system must be closed. As I mentioned before, we shouldn't have any external addition or loss of parent or daughter isotopes. We also need to use fresh, unweathered rocks to get reliable radiometric dating, because when we have our rocks exposed to weather or went through the chemical or physical weathering process, it is very likely that they will be losing or earning additional material of parent or daughter isotopes. By using the radioactive dating principles, radioactive dating method, we actually could identify the Earth's oldest rocks. And we know that the oldest rocks are found on the continents by using this method. All continents have rocks exceeding 3.5 billion years old. And the nice thing about this radioactive dating process is actually it helps us to confirm the geologic time. There is also carbon-14, which is another isotope that we can use for dating. We specifically call this type of dating as radiocarbon dating. And in this case, we use this carbon-14 isotope for dating geologically recent events because of its half-life, which is only 5,730 years. And we can use this method for dating the events as old as 70,000 years. Here in this picture, you see decay of carbon-14. So basically, carbon-14, which has atomic number of 6 and mass of 14, through beta electron emission, uh, turns itself into nitrogen-14, which is the more stable version of carbon-14. Carbon-14 is produced in the upper atmosphere from cosmic ray bombardment. In this picture, you see how nitrogen-14 can actually transform itself to carbon-14. In this case, with the cosmic ray bombardment, we add a neutron into the nucleus of the atom. And this absorbed neutron decreases the atomic number of the material down to 6 from 7. And it also keeps the atomic mass same, because what happens when we have a neutron captured, we are losing a proton. It is going to be emitted. So in this case, when we are losing a proton, that means the atomic number is going to decrease by 1. However, since we are replacing a proton by a neutron, the atomic mass is going to stay the same. Carbon-14 is a very abundant element in the nature, isotope in the nature, and it is actually basically absorbed by plants through photosynthesis or through our breathing processes. We need to keep in mind that carbon-14 is going to be only useful in dating organic matter. So when we have fossils, organic remnants, or some plant remnants, or some, say, tree remnants in the geologic material, in that case, we can use those remnants of the organic matter for carbon-14 dating. We know that all the organisms contain a small amount of carbon-14, including human beings.